Good afternoon, class. Today we are going to look at something called exponential functions, and probably from the title you can figure out it has something to do with exponents. So we're going to see some exponent rules today, and then we're going to define what we mean by an exponential function. This assignment, the first few problems are the foundation things, and then there's a point at which it changes from foundation topics to the college algebra topics. The first thing we're going to do today is define what we mean by a zero exponent. Ooh, ignore that little dot there. It's not supposed to be there. That's an A. Anything to the zero power is defined to be the number 1. So we're defining a zero exponent, and it says exactly what it means exactly what it says. Any number raised to the zero power is 1. We can do problem number 1 in the homework now. Let's do our first problem. Let me move this over here. Do this. I'm even going to open up my calculator because I'm going to use that in a moment. Oh, what is that? Let me clear that out. 47 to the 0 power. That's our first problem. And this is one of those classic times I've written it down, the problem, but it looks like I'm just writing the problem and writing the answer. The rule is that anything to the 0 power is 1. There's one exception. 0 to the 0 power is nothing. Not 0, it's just undefined. 47 to the 0 power, what do y'all think I'm going to write as the answer for that? 1. Anything to the 0 power is 1. I think everyone's number 1. The answer is going to be 1. 47 to the 0 is 1. I'll check it. And instead of doing instead of moving on, let me do similar question. Oh, this is a good one. -8 to the 0 power. Still a 1. Anything to the 0 power is 1. Sometimes students don't believe it unless they see it on a calculator. So here's my little calculator. I'm going to type in this one. Okay? Parentheses -8. It's popped up every now and then, but in this, right now I'm going to show you, this is the little key that you enter the exponent other than a square. Here's an x squared key and an x to the -1 key right there on my calculator. But to raise something to a different power, it's this little caret top symbol. Raised to the 0 power is 1. Be careful. Notice the parentheses around the -8. The order of operations, please excuse my dear Aunt Sally, says work inside the parentheses and then do exponents. Right here, there's no parentheses, nothing, so you do the exponent, and that exponent only applies to the 8. If you want to raise a negative number to a power, it has to be in parentheses. Look at what we get if we don't put the parentheses around -8. It's going to give me -1. So if you're raising a negative power, if you're raising a negative number to a power, make sure you put parentheses around them. Okay? Now, the next rules that we have, we're going to define what we mean by a negative exponent. Now, I'm going to state 2 ways of defining negative exponents. I'm going to write it as a integer or something that's not a fraction to a negative power, and then I'm going to define it for a fraction to a negative power. If we have a number a raised to the negative n power, a to the negative n, a negative exponent, that little red negative exponent means 1 over. A to the negative n is 1 over a to the positive n. I'm going to state the two rules. So if you have just a whole number to a negative power, you write it 1 over, and we'll see examples of that in a moment. And if you actually have a fraction raised to a negative power. So here's the second rule for negative exponents. If you have the fraction a over b to a negative n power, then that means flip the fraction. A fraction to a negative power means flip it. B over a to the positive n power. Okay? You'll get really familiar with these little exponent rules as you do these. And then you're going to be shocked to learn that logarithms, if you've never worked with logarithms, you're in for a treat on Monday, when we do logarithms. But logarithms are defined as exponents. That's why you got to know the exponent rules so you can work with logarithms. Let's do problems 2 through 6. Problem 2 says evaluate 1/3 to the negative 2 power. Okay. 1/3 to the negative 2 power. Well, I should have written the 1/3 in blue. Oops, y'all don't see what I'm writing. Sorry about that. This is a fraction to a negative exponent, so I'm using this statement right here. To raise a fraction to a negative exponent, you flip the fraction and then just raise it to a positive power. So here's what I'm thinking. If I flip 3 over 1, what do I get? Excuse me. If I flip 1 over 3, what do I get? 3 over 1. I don't really need to write that over 1, do I? But you flip. I just want to illustrate. You're flipping the fraction. That gets rid of the negative exponent and changes that. Oops. That wasn't an n. What was the a 2? Gosh, I'm messing up today. It was a 2 right there. 1 over 3 to the negative 2. I'm sorry. Why did I put an n there? So correct me, or tell me how I ought to correct this. It should be 3 over 1 to what power? Positive 2. That 3 over 1 I'm just going to think of as 3 squared, which is what? 9. So 1/3 to the negative 2 is just another way of writing 3 squared. Okay? So 9 Oh, here's a good one. This is problem 3. 4/5. Don't help me. Let me see if I can write it correctly. To the negative 2 power. Let me check to make sure I didn't miss coffee. Okay. 4/5 to the negative 2 power. Is this hard or not so hard? We're raising a fraction to a power, a negative power. So that means flip the fraction and use the positive exponent. Flipping the fraction makes the exponent positive. So we now have a positive 2. And y'all can square 5 over 4. What's 5 squared? 25. And 4 squared is 16. 4 times 4? 25 over 16. Oops. So 25 slash 16. Any questions? Y'all following me? Y'all following what we're doing?
I got mixed up for a second.
Oh, you got mixed up on which one? This one?
Uh-huh.
Okay. If it's a fraction raised to a negative power, here's the rule: a fraction to the negative power. Flip the fraction and use the positive power. So 4 over 5 to a negative 2 power is the same thing as 5 over 4. I flipped it in a positive power. That's what I did here. The 1/3 to a negative power, I flip it and use the positive power. Let's make a note. Flip. Okay. Any questions? Are we ready for number 4? B to the negative 9 power. What do the instructions say there?
Rewrite using a positive exponent.
Okay. This is one of those problems that you can complain and say, it looks like he just wrote down the problem and wrote down the answer, because it sort of is what I'm going to do. B to the negative 9. Show my paper. See, problems 2 and 3, those were fractions with negative exponents. So we use this rule over here. But on problem 4, there's no fraction. So it's this rule here. B to the negative 9. A negative exponent, that red negative, means a red 1 over. That's what I was trying to show here using the color. The red negative exponent is a red 1 over. And then this b to the positive 9. 1 over b to the positive 9. Any questions there? And if you're thinking, wait, where's the work? It looks, yeah, not any work to show. All the work is up here. Okay? I'm going to type it in. 1 over b to the 9. Be careful, don't make that a 6. 1 over b to the 9.
Any questions?
Mm-hmm. Oh, wow. That's not a really good example, is it? 1 over 7 to the 7. What are they?
Rewrite using a negative exponent. You're going backwards now.
Yeah, remember I've said, in algebra you always do it one way, then you do it the other. Like you FOIL, then you factor. Okay? So 1 over 7 to the 7. That 1 over, I'm going to look at this rule here. Go backwards. How would I write this with the negative exponent. Well, a negative exponent means 1 over. So, anyone have any idea of what I'm going to do to write it with a negative exponent? I'm going backwards from this rule. Looking at it from right to left, the red 1 over is the same thing as the red negative exponent. Having said that, does anyone have any idea of what I'm trying to say the answer is here? 7 to the negative 7. It's unfortunate that there's 2 7s here. It might make it a little bit trickier than it really is. 1 over 7 to the 7 could be written as 7 to the negative 7. Oh, that's terrible. Actually, it's not terrible. Okay. Okay. Number 6.
The same instructions. They want you to rewrite this thing using a negative exponent instead of a fraction.
So what is that? 1 over z to the third?
Yes.
Is this hard or not too hard? What do y'all think?
Not too hard, just different.
So 1 over z to the third. How am I going to write it? Oh, there. With a negative exponent. Well, a negative exponent means 1 over, so I'm going to drop the 1 over and write what? Z to the negative 3 power. Good. Not a lot of work to write out here on these first few problems. I'm sure they're happy to hear me put the qualification. Not a lot of work
On
these first few problems. Oh, and also this is the longest assignment in case you didn't know that. Oh.
Rational exponents. Okay, time
Oh.
to talk about
Oh, okay.
some more properties of exponents to study.
Yeah, let's discuss we've already stated these, I think it was at the time of the 4th assignment.
Square roots,
5th.
equations, and
Yeah,
cube root equations.
I'm going to define what we mean by a fractional or rational, is what they're usually called, exponent. I should probably use b as a variable because the little things are called exponents.
Or power.
But do y'all remember what this thing is called? Like here, 47 to the 0. What do you call the 47?
The base.
Base.
The base
Is what I'm
of the
Yeah,
exponent.
the base and exponent. So a lot of times you'll see b used. I'm just trying to avoid b as much as I can so it doesn't wind up looking like a 6.
You know, that's going to be a problem because when I'm dealing with exponents, I use b as a variable.
Yeah.
Okay, so I'm going to have to modify my law once I take over the nation. Yes.
I'll use b here.
Okay, you're right. B.
Okay, we've saw, oh gosh, a couple of months ago, almost, that a 1/2 exponent is the same thing as a square root. So b to the 1/2 is the same thing as b, the square root of b. So this red 1/2 exponent is the same thing as this red square root. A 1/3 exponent is a cube root. A 1/4 exponent is a fourth root, and so forth. In general, we say this: b to the 1 over n power is the nth root of b. So, oops, black b, not red b. There is no red b. Oh, that's pretty good. Okay. So,
Here's one.
yeah. If you're wondering to yourself, wait a minute, what happens if that top exponent, if it wasn't 1 over? I'll show that in a moment. Right now we're looking just at exponents in the form 1 over a number. So what's number 7?
Rewrite without a rational exponent, x to the 1/4 power.
Mm-hmm. It's just the formatting. I would prefer if they wrote the 1/4 exponent sort of like this, with a slanted bar, rather than the way they have it. Well, okay. Have I said enough for us to do number 7? How do we write this x to the 1/4 without the 1/4 exponent? Well, a 1/4 exponent is 4th root of x. 4th root of x. I should circle that.
Okay, we go to the nth root hot button, the radical that has 2 blue boxes, because up here you have to type that 4, underneath there, x. Here's another one. 64 to the 1/3.
64 to the 1/3. Now, does it say simplify your answer?
Right, let's see.
Or what does it say?
I need to read those
Read them.
directions. Rewrite without a rational exponent and then simplify if possible.
Let's see. Okay. A 1/3 exponent is the same thing as a cube root. Okay? So, cube root of 64. Since there's a number under that cube root symbol, maybe we could reduce it.
Ask yourself.
Don't say 8. The square root of 64 is 8.
But what number do you cube to give yourself 64?
Oh, 4? I agree with that. 4 times 4 is 16, times another 4 is 64.
And that's because 4 cubed is equal to 64. What number can you cube to give yourself 64? 4. Now I'm turning on my microphone, but the battery is
That's
very
why I was
low.
trying to give you mine.
But I'm not gonna switch it. I want to run these batteries down until they're dead. I don't like the idea of throwing them away when there's still some charge in them. Okay, the planet's dirty enough as it is, so try to use everything up as much as possible. Oh, you opened up that calculator.
I wanted to show how to punch this into your calculator.
Okay.
If you went
sorry.
64 raised to that 1/3, if I go 1 over 3, is that going to give me the answer 4?
No, it's going to give you 64 divided by 3. If you want to punch that into your calculator, that fraction 1/3 needs to be enclosed in parentheses to make sure that your calculator takes 1 divided by 3 and then raises 64 to that. So, next problem.
Well, you had to type the answer.
4.
Oh, wait, no, you got to tell them.
Oh,
So
okay.
now we need a rule of what to do if the top number in the exponent isn't a 1. So here's a new rule.
Notice in these statements here, the exponent's numerator was a 1 in all of them. Suppose it's something other than a 1. If we have a base raised to the a over n power. A fractional exponent means a radical. So suppose that numerator is something other than 1. You still have an nth root. You still have the nth root. Let me write that radical.
And the number on the bottom is that root.
The base b, that's what's underneath the radical. And you have two options with that numerator a. You can either put it underneath the radical, which is not my favorite approach, because b to the a could get pretty big. Okay? The method that I like is to express it. It's the nth root of b, the nth root of b. You simplify that nth root, and then that numerator a you can put as an exponent on the outside. And this is the format that I prefer right here, this one.
This top number is the power, the bottom number is the root. You'll get smaller numbers if you do the root, then raise it to the power. And that's what we're doing on number 9. 16 to the 3/4 power.
This is number 9, 16 to the 3/4 power. Okay, that denominator says we're going to have the 4th root. What will go underneath the radical? 16. The base becomes the radicand. And then realize if you took that 3 and you stuck it underneath the radical, 16 cubed, 16 times 16 times 16, that number's getting mighty big. That's why I said I prefer to put that numerator power on the outside. Put the 3 on the outside. So work underneath there. The 4th root of 16. Here's what you're asking yourself. What number to the power 4 will give you 16? Don't say 4. 4 times 4 times 4 times 4 is 256. So what number do you raise to the 4th power to give you 16? I think I heard it. 2. I agree. So we have a 2, and on the outside we have a power of 3. Notice we were able to do all this with small numbers. If you'd stuck that 3 underneath there, 16 cubed, that would not have been a small number, and then you would have needed the 4th root of that. So my advice, stick the numerator power outside. Now look at what we have. The 4th root of 16 is 2. 2 cubed, we get a final answer of
2 times 2 times 2, don't say 6.
8.
8. 2 times 2, 4 times 2 is 8. See, if you'd cubed the 16 first, you'd then be looking for a 4th root of 4,696. Turns out to be 8. Did y'all know that? The 4th, if you multiply 4 8s together, you get 4,096. Huh. But
Okay.
notice, nice small numbers.
Nice small numbers, that's right.
8. We're trying to move fast because it's a long assignment.
This is
and
a
we're
long
doing
assignment.
Every one of them today.
Number 10.
We ready for the next one? Any questions?
Oh, hold on.
16 to the 5/2 power.
Oh, that's a good one. 16 to the 5/2. Okay. What sort of radical are we going to have here? What do we look at to decide on the type of radical? The top number or the bottom number? The bottom number. That 2 says we're going to have a square root.
Notice with the square root, you don't write the little 2 there, but it's assumed. Okay?
And once again, why do we not write that 2 there? Because think back to the olden days, before modern equation editors. It was a nightmare trying to get those little indices typed on those radicals. Think about those old-fashioned typewriters. You couldn't change the size of that number. You'd press that 4, and that 4 would be one size.
They don't know about the
so much of this
typewriter.
Oh, wow. Okay. And where am I going to put that 5? On the outside. So
we
what
can
will I
all of
do
this without a
first?
calculator.
What will I do first? The square root of 16. I think we're going to need a calculator, Tony. I was about to say,
right.
You can do it without a calculator, but I want a calculator here, because now what do we have to do? We knew the square root of 16 was 4, but what are we going to have to do now with that 4? Yep, 4 times 4 times 4 times 4 times 4.
4 times
Well,
4
4 to the
16.
4th is 256. 256 times 4, is that 1024?
Yeah.
Are you just trusting?
Yeah, I'm
okay. But once again, if you'd put that 5 on the 16 to the 5th, that would have been a huge number
There
to
it
work
is.
with.
And then take the square root of that answer.
Any questions there?
Oh, let me type it in.
Yes.
So on the 5/2, why didn't you put the 2?
If you don't see a number there with square roots, we don't show that 2. With square roots, it's just standard. If you see
You
a
say
radical
it. You
and you
say
don't,
square,
you say square, but
you don't have to
you don't
write it.
write that 2 down. Okay.
If this were all stuff being invented right now, we'd put the 2 there just because it's so
It's
easy
easy to
type.
type it now,
Yeah.
but back in the
then.
olden days,
And there were probably more square roots being typed than anything else.
oh yeah. Well, they made sure of it. They didn't bring in other stuff. They tried not to use other radicals.
24.
Mhm. Any questions? Y'all are certainly quiet today. I don't know what went on in here before I
They're
arrived.
just dumbstruck by my excellent teaching talent. They told me I was gifted. But
Number
I paused
11.
it during that so that they would have.
So the tape's going to be messed up.
It's not a tape.
I mean, so the recording's going to be messed up. Oh, I guess you have all the answers, don't you?
Oh wow!
That's what you
Rewrite it
say.
with rational
If you want to win an
excellence.
argument with somebody and get in the last word, well, I guess you know everything. I guess you have all the answers. Okay, I'm waiting for y'all to tell me. How am I going to rewrite this? They want me to rewrite it using a fractional exponent.
Oh.
Switch to my paper. Is this going to take a lot of steps? No.
You're going backwards. Look at these rules up here. Do the
square root of b.
right to left.
It's the same thing as b to the 1/2. So the
Red
square root of
square
5, that square root disappears and becomes an exponent of 1/2. So 5 to the 1/2 power.
I wonder why would we ever want to write it like that? Well,
We will.
on
That's
Monday.
going to be one of our tricks that you're going to start using when we start logarithms. Anytime you see a radical, you're going to have to rewrite it using an exponent. We're not going to be going exponents to radicals. We'll be going the other way around. You'll see a logarithm with a square root or a cube root. You got to rewrite it using an exponent. Did you type the answer in?
Nope. 5 raised to the 1 over 2.
Any questions there? One more, number 12.
Oh, this is a good one.
The fourth root of 19.
Rewrite it with the rational exponent.
That means don't use a radical, write it using an exponent. Okay?
And it even gives you a hint. It's going to be a fraction. Well,
Yeah,
fraction.
rational, they're saying it's going to be
That's good.
Yeah. So, here's my 19. What else do I need?
Back.
The 1/4 exponent. A fourth root is the same thing as a 1/4 exponent.
Just like a cube root is a 1/3 exponent. A
For
square
a final
root is
answer of
1/2.
19 to the 1/4.
19.
19, use your exponent button. Once again, they call it a superscript rather than an exponent, but this is
19 raised to the 1/4 power. They say simplify your answer, you can't.
you can't. 19's a prime number.
Yeah. Sometimes. And they say simplify if possible.
If possible. Mhm. Any questions there?
So the name of this is exponential functions.
Okay, you
but
better switch over.
so
I got to
far we
do some
haven't had a
writing.
function yet. So we'll start some functions now.
Okay. Our definition of exponential function. When I'm using the letter B from now on, as we move into logarithms, the same statement's going to be true. We're going to assume that the letter B is a positive number and it doesn't equal 1. That is a B, unfortunately. B for base. Let's see, how do I want to write it? An exponential function to the base B is any function that can be written in the form y equals or f of x equals base to the power x, where x is any real number. I'm just putting an x up there as the exponent, but it can be any expression containing an x. I guess I really should have said b to the g of x, but that just makes things messy. What's important here, we have not seen anything exponential this semester. We've seen things like x squared and x cubed. Now we've even seen things like x to the 1/4. But the variable has been the base at all times. The power has been a number. That is no longer the case with exponentials. The exponent is where the variable is located, okay? I'll make a note. Exponent contains variable. That's what makes it exponential. Exponent contains the variable. Instead of things like x squared, we're going to be seeing things like 2 to the x or 3 to the x. The variable is where the exponent is located. First thing we're going to do is we're going to graph exponential functions.
Write down the two general shapes. Like this or that.
Okay. Well, you'll hear, yeah, I'm sure you've heard of exponential growth and exponential decay, if nowhere else than in your science classes. You know, exponential growth, population is exponential. It grows, the human population, it grew very, very, very slowly, okay? It was almost flat for centuries and centuries. And then it started changing. It started growing more rapidly, and now it's growing extremely rapidly. During my lifetime, are we at 8 billion yet? The population, yes. So it was 3 billion something when I was born. Out of all the years of existence, there were only 3 billion people on this planet when I was born. Now we've got 4 billion, 5 billion, 6 billion. Think about it. The population has grown by 5 billion during my lifetime. But this is an example. This graph is the standard shape of exponential growth. You have one side extremely flat, almost horizontal. The other side extremely steep, almost vertical. The other possibility when you're looking at exponential decay, I'm thinking of maybe a radioactive isotope, Chernobyl over there in the Ukraine. That radiation there, it's decaying, but it's decaying slowly. It's still going to be there when you're dead and your grandkids are dead and your great-grandkids are dead. It starts decaying and it decays very slowly. And then after millennia, after thousands of years, eventually there'll be very, very little there. It'll be almost nothing, but there'll still be a trace. It'll never get down to zero. Here's an example of the general shape of exponential decay. Exponential decay. When you're drawing these exponential functions, you should expect one side to be real flat,
Almost horizontal.
almost horizontal. The other side extremely steep, almost vertical. Okay, so now we're going to graph one. Let's draw a graph. Let's see. Number 13.
14.
Number 14? Why is it 14?
No, 13, yeah.
Oh, I don't know. Okay. I'm going to go to another page. This is number 13. They want us to draw the graph of y equals 3 to the x. And you'll notice there's not an exponential graphing tool in this assignment. The graphing is just done by hand and then multiple choice. I think Tony and I are the only ones that like those graphing tools so much anyway. Most students seem to prefer the multiple choice
Knowing
stuff.
the shape of the exponential growth and decay,
You know
are there a
something?
couple of these you could, if
I
you were
think
going to
there's-
guess?
I think there's 3 that you could just knock out, knowing that it's going to look like one of these 2 graphs, either the exponential growth or exponential decay. Which one?
If you had to guess, what do you think it's going to be?
A is the only one that looks like
He
one
doesn't
of those
look
2
like it,
possibilities.
does
But here's what we're going to
like
do.
that.
Remember I said that the exponent can be any real number you want to. We're going to graph exponential functions just by plotting points. You already know the general one of 2 general shapes. You just have to figure out which one is it. Is it rising from left to right, or is it falling? Is it or the y values growing, or are they decaying? My advice to you, just make a table of values, and if you use the integers from 2 to -2, you should get a very good picture drawn. And from there you can figure out the shape of the graph. We'll start off with the 2. 3 squared. What's that going to give us for the y value? 9. Okay, I agree. 3 squared is 9. 1. 3 to the first power. What's that going to give us? 3?
3.
Okay. What about when we plug in 0? Be careful. Remember the first thing y'all did today. 3 to the 0 power. What does that give us? The definition of 0 power, a non-zero to the 0 is defined to equal 1. Now, -1. This is where you better remember that stuff about negative exponents. In place of that x, we have 3 to the -1 power. What is 3 to the -1 power? Where did he define negative exponents?
Right here.
3 to the -1 is the same thing as 1 over 3 to the +1.
Third. Alex
One-
is really on it today.
Yep, which is 1/3. What about 3 to the -2? 3 to the -2, that would be, I'll get it started, 1 over 3.
To the second squared.
So that reduces to 1 over 9. I agree.
3 squared.
Notice something. As we get x values that are negative, notice how small the y values are getting. You did go up 1/3. Now you're going up 1/9. You're going up less and less each time, but a non-zero number to any power will never be 0. It'll never be negative. And the base has to be non-negative. Remember I said that the base has to be positive. So a positive number to any power will always be positive. Positive any power will always be positive. Let's draw our XY grid and plot these points.
Now, when they're doing this later, they'll probably just, once they have the points, look at the graph.
Hey, look at this. I'm putting the little tick marks down here below the x-axis, but do I expect to have any in my graph down here? A positive number to any power, is it going to give us a negative y value? The graph will be entirely above the x-axis. So we're at right 2, up 9, right there. Right 1, up 3. Then 0, 1. That's our y-intercept. That's where the graph is passing through the y-axis. Then -1, we move up 1/3. So we go left 1. Imagine breaking that little interval there into 3 equal units. It'll be somewhere right out there. At -2, we're only moving up 1/9. Imagine breaking that interval into 9 equal subintervals. We'd be even closer to the x-axis. If we had plugged in -3, we'd only move up 1/27th of a unit. We say that this figure is getting closer and closer to the x-axis, but it's not passing through, and it's never going to touch, because if it touched the x-axis, that means the y value is 0. And a positive number to any power will never be 0. It will always be positive, which means greater than 0. We say that the x-axis in this event is a horizontal asymptote. Horizontal asymptote. asymptote.
Running beside
It's running right beside it. Now, it'll get to the point where it looks like the curve is just sitting on top of the x-axis, but there'll always be a fractional amount of space there, okay? This is like when the Earth was formed and human beings came along and started reproducing. For centuries and centuries, the population didn't grow any at all. It just sat there practically the same. But eventually, it took off and it started growing very, very rapidly. A, B, C, or D?
They said they knew it was A without doing any of that.
Okay. Number 14.
Exponential growth. Hear this more.
Y equals 2 to the negative x. Once again, I'm going to make a table of values, and I'll use the integers from 2 to negative 2. And that should be enough to get a good picture drawn. Let's start off down at the bottom this time. You take the 2, you have 2 to the negative, plug in that negative 2, what's about to happen there? 2 to the negative 2. What's going to happen here? That becomes a positive. So 2 to the 2 squared gives me a 4.
Alex, I couldn't hear you.
I couldn't hear what you were saying, Alex. A good teacher techniques, okay? For the student that always answers correctly, on that rare time when they finally make a mistake, you pounce.
No.
Pounce on it, okay?
No,
I'm joking. That's
couldn't
a bad
hear-
teacher. I couldn't hear what you were saying. I'm sorry.
Huh?
1 over 4.
Oh, yeah, he was doing this one.
Oh, you were doing the other one.
Positive.
Oh, okay. You want to start up at the top?
Yeah, that's where I normally start.
I was going to deal with the negatives first, okay? So we have a 2 to the negative, and then I plug in that negative 1. That negative, what's that about to become? Isn't that just going to be a positive 1? 2 to the first power is 2. Now plug in the 0. Well, that's nice. It's just 2 to the 0. We know what that equals. 1. That's our definition of 0 exponent. Now, plug in the 1. We have 2 to the negative 1. 2 to the negative 1. How am I going to rewrite 2 to the negative 1 without a negative exponent? It's a negative exponent, so I'm about to pick up what? It's a negative exponent, so I'm about to pick up that 1 over, and then it's a 2 to the first, which is just 1/2. Now, Alex was telling us what we get if we just plug in a 2 here. That's going to be a 2 to the negative 2, which becomes a 1 over what? 2 squared, which is 4, so 1/4. Any questions on our calculations there? I'm not going to bother plotting a lot of points. As a matter of fact, if you know the general shape, you know it's going to either be going up or it's going to be going down. One side will be flat, the other will be real steep. If you know that, then generally 3 points are all you need. I'm going to use the right one up a half. I'm just sketching out a rough sketch. Right 1 up a half. Then left right 0 up 1. So you're on the y-axis. And then left 1 up 2. Well, it looks like the steep side. Is the steep side going to be on the right or on the left in this case? Where will the steep side be? On number 13, the steep side was on the right. Where is it going to be in this one? We start and we connect. The lower side has to be real flat, close to the x-axis. What has to be happening here? It has to be going up real fast. So in this case, the steep side is on the left, the flat side is on the right. If you know those general shapes, you can really get by with just 3 points. Any questions there?
Let's see, right, which one? Let me see. I'm thinking it's not A.
Not A.
It's
Not B.
No. Oh, well,
I know that's C.
Oh, there's not even a letter.
Oh, you're right. Is that it? No.
Tell me when to stop.
That one.
It's this
Ah,
one here.
Yeah. Notice. Okay. Left 2, up 4. They showed that point.
Left 2, up 4. You're right. Left 2, up 4. It would have
Left
been
1,
up there.
up 2.
Okay.
Over 0, up
Okay.
1. Now, we are back to begin. Okay. Need to talk a bit.
So we're doing 2 things with exponentials today. We're graphing them. That's what we just finished doing. And my advice for you, just plot points. Just plot points and use your properties of exponents. You don't need a lot. The integers from 2 to -2 for x would be fine. You can probably get by with just 1, 0, and -1. The next thing we're going to do with exponentials is solve exponential equations.
Solve quadratic equations. Solve rational, radical. You know what?
First of all, let's make sure we know what an exponential equation is. An exponential function is a function where the variable's in the exponent. An exponential equation is an equation with a variable in the exponent. There are 2 generally accepted methods of solving exponential equations. The first one, I think I'll Roman numeral these things. Roman numeral 1. The first one is the same base method. The same base method says if b to the x is equal to b to the n, then if the bases are equal, then the powers have to be equal. Then x has to equal n. And if you stop and you think about that, let's say 5 to the x is equal to 5 squared. The bases are the same, 5 and 5. What's the only thing that x can be if it's going to equal 5 squared? That's the only number you can plug in for x to make the left side equal the right side. It should be obvious. Could I plug in a 3 and the left side equal the right side? Could I plug in a -7? If the bases are equal, then what? The powers have to be equal, so x has to equal 2. The only number you can plug in there for x is x equals 2. Of course, the problem is, with the equations they're giving us, we're not going to have the same base on both sides. You're going to have to use your properties of exponents to get the same base on both sides. And that's what we'll be doing the rest of this class. There's a second method of solving exponential equations where they're unlike bases. Say 3 to the x equals 5 squared. It's impossible to get the same base. I'll say unlike bases. That method requires the use of logarithms. You'll see that 1 week from today, or will that be?
No.
Well, in 2 assignments, you'll see problems like this. With unlike bases, you have to use logarithms.
Everything we're doing today in this assignment is rigged to work out with
Same base. You should be able to get the same base. Here's an example. Don't wait a minute.
Oh.
Here's something. Suppose 3 to the x equals 5 squared. 3 and 5 are both prime numbers. You can't write 5 as a power of 3 using integer powers. Likewise, you can't write 3 as a power of 5. This thing here, you cannot get a common base, so you would have to use logarithms. I'll say no like base. But we'll see that in not 2 weeks.
Which one did we think is the best one? I think 16 is the best.
16 is the best one to get started with.
And then we'll go back to 15. But this one sort of illustrates the thought process.
3 to the 2x minus 7 is equal to 81. The work here is that you have to get the same base on both sides. You say to yourself, well, there's only one base, 3. No, 81's a base 2. I don't see a power there, but there's an assumed power of 1. There are 2 bases, 3 and 81. My advice to you, start with the smaller base and try to rewrite the big base using that smaller base. For example, 81. I need to write 81 as a power of 3. 3 to what power? 3 to what power will give me 81?
Let's just start multiplying with the calculator. How many 3's do I need to multiply together to get 81?
Well, 3 times 3 is 9.
Times 3 is 9.
Times another 3 is 27. Times another 3.
What about 4?
Is that it?
If we multiply 3 4s, is that the same thing as 9
times 9? That should give it. There it is. So we can rewrite 81. We have 3 to the 2x minus 7 on the left. And on the right, 81, that's the same as 3 to the 4th power. Any questions on my logic there? And you have to get the same base on both sides if you're going to use the same base method, and that is all we have at this point. We have not seen logarithms, so any equation they give us, we're going to have to be able to get a common base using properties of exponents.
And you see how that one differs from right up here? There's no way you're going to get a 5 written with a 3.
3 to the
Base.
first power is 3. 3 squared is 9. We skipped right over 5.
Okay.
Sometimes it's just impossible to get a common base, and we'll see those problems will require a calculator and logarithms. But here, we got a common base. If the base is equal, then the powers have to be equal. So, once you have the same base on both sides, no parentheses, just base to a power equals same base to a power, we drop the base, you set the exponents equal. 2x minus 7 has to equal 4. Once the bases are equal, you drop the base, set the powers equal. And then it's a matter of solving a linear equation. We know how to solve this. What am I going to do first? I want to get x by itself. What will I do? Add 7. That's going to give me 2x equals here. Pardon me? No, I think it's going to be a 4. Remember, it's 4 plus 7. That's an 11. And then, what will I do? Divide by 2. Divide by 2 to give me x equals 11 halves. You're going to have to use your properties of exponents to get the same base on both sides. And once you have the same base on both sides, you drop the base, set the powers equal.
Okay, so
Any questions
over
there?
2.
Well, we're going to be doing quite a few of these, so let's see another one. Let's go back to number 15. Solve the equation 36 to the x is equal to 6. This is number 15. 36 to the x is equal to 6. I have two different bases here. What are they? 36 and 6. Okay, well, I don't see a power on this 6. Well, that's just a 6 to the 1 power. Let's take the small base and try to rewrite that big base as a power using that small base. This isn't too bad at all. 36, how can I rewrite that as a power of 6?
6 to what power gives us 36?
6 to the 2 power. There's something called the power rule of exponents. We haven't used it today. I don't think you didn't use it, no. The power rule of exponents says that if you have a power raised to a power, say you have b to the x raised to the n power. If you have a power raised to a power, you keep the base, but you multiply the powers. B to the x times n. If
What
you
are
have
you
a
telling them to do here with this 2 and x?
A power raised to a power, what are we going to do with that 2 and x? I need it written just as 6 to a power equals 6 to a power. No parentheses. So, what can I do here to get rid of that 6 squared to the x? A power raised to a power, we will. A power raised to a power, we have to multiply 2 times x, gives me 2x. And this is called the power rule of exponents. There's even a power rule of logarithms, that's a restatement of this. It's one of the more bizarre properties of logarithms. But for us, a power raised to a power, you multiply to write as a single power.
Are we through with the sixes at this point?
We have 6 to a power equals 6 to a power. We have the same base on both sides, so we drop the bases, set the exponents equal. Once you get that common base of 6 without any parentheses, the rest is real easy. What are we going to do to solve for x? Divide by 2 to give us x equals 1/2 for my final answer. Any questions there? Add this power rule to your bag of tricks, because what you're going to be running into powers raised to powers, that means you're going to have to multiply to get a single power.
1/2. Okay,
Number
what's
17.
Oh,
Se- Okay, number 17, we have 2 to the 2x minus 1, 2 to the 2x minus 1 is equal to, what's the other base? 16. We need to write the big base as a power of the small base. So we have to write that 16 as 2 to a power.
How many 2's are we going to have to multiply together to get 16?
How do you write 16 as a power of 2? What exponent am I going to put on this 2 here to make it equal 16?
2 times 2 is 4.
2 times 2 is 4. 2 times another 2 is
times another 2 is
8. Times another 2 is 16.
Yeah.
2 to the 4th.
4, that's the same as 4 times 4, isn't it?
Any questions on my logic there? Because once we've done this, we have the same bases on both sides. We drop the base, set the exponents equal. 2x minus 1 has to equal 4. Your goal is the same base on both sides. If it's impossible to get the same base on both sides, well, we'll see how to do that next week. That's going to require logarithms.
It won't be next week, week after next. Next week
Okay.
is logarithms.
Add 1 to give us 2x equals 5, and then divide by 2 to give us x equals 5 over 2 for my final answer.
Oh, look at that. Good example. 5 over 2.
Generally, you want to start off with the small base, try to write the big base as a power of the small base, and you may have to play around on your calculator a little bit. But you have a starting point. At least you have a starting point. 2 is a prime number. You can't change 2. You have to change the bigger one if you're going to get a common base, and you have to be able to get a common base, or else you don't know how to do these problems.
Is it 18 next?
20.
Oh, 18. This is a doozy.
Okay. 16 to the 3x minus 3. 16 to the 3x minus 3 is equal to 64 to the x plus 3.
The natural question to ask when he was doing that last one, but what if that you didn't have like a prime number on one side?
Well, 16's the smaller base. Well, 16 to the first is 16. 16 to the second power, is that 256? Where's that calculator you're always using, Tony?
Yeah, 16 squared is not 64.
I think it's 256. We just skipped right over 64. So we can't use the small base as the common base.
Right over here,
Sometimes
16 to the
16
question.
to what power gives you 64? Nothing. 16 to the first is 16. And 16 squared is 256.
So it's some number between.
It's somewhere between 1 and 2, that number, but it's not an integer. We're just stuck. We can't use 16. Sometimes you have to change both sides. When I see 16, I ask myself, how can I write that as an exponent? 16, something pops up real fast in my head. What times itself gives you 16? 4? I think we can use 4 for both of these.
4 times 4.
Okay, let's see, that's it. We know that 4 squared is 16. This seems so familiar to me. We may have run into this some other time here.
Today?
Yeah, I think so. This maybe we need a cube root of 64 or something.
Okay. But
What could 4 cubed gives me 64.
multiply.
Sometimes you have to change both sides.
And if that
and
happens, you start with the small base.
Start with the small one. Write it as a power, then using that same power, try to write 64. Here's something that's interesting about this problem. You could have used a 2. You could write 16 as 2 to the 4th, and then 64 would be, 2 to the 6th. But I think it's cleaner to use a larger base. 4 squared is 16. 4 cubed is 64.
Start with the smaller. Don't start over here because you might think 8 squared. Well, no, you can't
8.
write 16. It's 8 to a power.
You start at the smaller one, write it using an exponent, and then try to write the big one using the same power. Now we have powers raised to powers. What are we going to have to do there? We can't drop the 4's yet. You can't drop those bases until there's no parentheses. Just base to power equals base to power. What are we going to have to do? What are we going to have to do here when you have a power raised to a power? You multiply
Yeah, to remove
a power raised to a power, you multiply, but this time, look at what you're going to have to multiply. You're going to have to multiply 2 times 2x minus, 2 times 3x minus 3. What are we going to have to do to multiply 2 by 3x minus 3? Distribute the 2 there and there. 2 times 3x gives us a 6x minus, what else? 2 times 3 gives me another 6. Distribute the 2 to get a 6x minus 6. Now we have to repeat it on the right side. We have a 4 cubed raised to the x plus 3. Power raised to power, so once again we distribute that 3 there and there. What's that going to give us? 3x, keep going, plus 9, yes. Now what can we do?
Are we going to write the number 4 now? Or are we through with those big 4s?
We have the same base on both sides. Base to power equals base to power, so we drop the base, set the exponents equal. I'd subtract 3x from both sides. 6x minus 3x gives me a 3x equals, how about adding 6? What's that going to give us? 15. And then I will divide by 3 to give us x equals 15 divided by 3 is 5. For my final answer. Sometimes you have to change both sides. Any questions there? Okay, I need to write some before we do more problems.
Wait, did I punch it in? I did.
Yeah,
right?
you did.
Yeah.
Okay. Recall that an irrational number is a non-repeating, non-terminating decimal number. I suppose the most famous, well, now when I say non-repeating, I mean it's not repeating the same block of digits over and over. It's not a 0.33333, well that's 1/3, that's a rational number. And it's not repeating 0.251251. It's not repeating the same block of digits over and over, and it never ends. Since the digits never end, to express the exact value of an irrational number, it's impossible to write out all the digits, so we have to use symbols. I suppose the most famous example of an irrational number is the number you get when you form the ratio of the circumference of a circle to its diameter. If you take circumference divided by diameter
Of any sort.
of any circle, you get a number that's approximately 3.14. What do we call that number? Pi. Yeah, there's the most famous example, pi. But it turns out we've been working with irrational numbers since the first day of the semester. Any square root that's not a perfect square is an irrational number. That's why square root of 2, we have to write it like that. Square root of 3. What about the square root of 4? Is it irrational? No, that's a 2, but it's an integer, okay? But the square roots that aren't perfect squares are irrational numbers. There's another important irrational number. It's called the natural exponential.
Google calls it Euler's number.
The natural exponential, and it was, I guess you could say, for lack of a better word, it was discovered by Euler, a famous mathematician, and he discovered the number, and so he decided he would use an E because his last name started with an E, okay, for Euler. So we have to use a symbol, and it's approximately 2.718, and that's good enough.
No,
okay.
keep going.
Okay.
2818.
2818.
45.
4. All of a sudden, for a moment, it looked like it was going to start repeating the same block of digits. Okay, in which case it wouldn't be irrational, but the digits do start appearing randomly after a while. So you don't need to know that decimal approximation. What you need to know is that E is an irrational number. If you have a base that's E on one side of the equation, you better have an E base on the other side as well. To illustrate, number 18, the letter E, the lowercase e, is no longer a variable for our purposes. That e is representing a number. We have e to the 10x minus 1 equals, is my microphone still working? I can't believe this battery is still holding out. But I've started worrying about how you dispose of batteries. That's why I'm just adamant. I want to use it up until there's absolutely not a bit of power
And
left.
then I'm gonna give it to the college.
Then we'll leave it here in the classroom for the college to dispose of it in a environmentally friendly way.
I'll bring it to my office. And
Well, I know what you're going to do if you bring it to your office, Tony. You're going to leave it there, and in 10 years when we retire, we'll just leave all those batteries there and let the college
it could be a
decide
really
what to do
mess
with
by
them.
then,
I think it would be. It'd be a toxic waste dump, probably. Okay.
maybe. So all that talk about E, just to say,
If E is the power on a base on one side, you better have an E on the other side.
if you don't,
Because you
you'll
can't,
know how
if
to
you
do
don't
it
have
week
an
after
E,
next.
if you don't have E's on both sides, that requires the use of logarithms. This is the natural exponential. So we have an exponent that's natural. We have an equivalent logarithm. The natural logarithm is what we would have to use if you didn't have E's on both sides. But here, getting a common base, we have it. The only problem is we have parentheses. We know what to do when we have a power raised to a power. What am I going to do with this power raised to a power?
In algebra, to get rid of parentheses, you usually do what? Starts with M.
A power raised to a power, you multiply the powers. 8 times x is 8x. And now we have the same base on both sides. We drop the base and just set the exponents equal. It couldn't get easier. If you have an E as a power on one side, you better have an E on the other side. Otherwise, you cannot get a common base. Oh, let's see. How about we subtract 8x from both sides? 10x minus 8x, what's that giving me here? 2x equals, and then here, what's going to happen? Okay, I'm moving the negative 1 over. That's going to make it a positive 1. I got it here. Oh no, I'm half deaf. I don't deny it. Okay. I couldn't deny it if I wanted to. So to give me x equals 1/2. If I were the kind of person that would blame somebody for that, I'd have to blame it on our father, with his love of loud music and at a young age, instilling that into us. So, to make us think that was important.
Yeah, I know.
Shame on him. Daddy, you hear that? Daddy, you hear that? Just in case. Any questions? We need a little humor here. Y'all seem I don't know what Tony did at the beginning of class to put the fear in y'all. Y'all are so quiet today. It's a little alarming.
We could tell you we would, but we just can't.
But he
can't.
threatened
I
you,
threatened
didn't
him.
you? More great pedagogy techniques from Anthony Precella. Okay. Number 19.
Oh, wait. I've looked through these to make sure. Okay, no, it's not the same
It's
thing.
not the same
These
thing.
problems look so similar. Like 22 and 23 were the exact same thing. So I did it probably foolishly. I should have just. Is this one similar to the one we just did? Could y'all
Okay.
talk us through on it?
Yeah. I think this is pretty similar. Could y'all talk me through? Tell me what I'm going to do first. Okay. The 8 up here, we did the 8 times x. Here's the 6 times x. So we have e to the 8x minus 1 is equal to e to the 6x. And now what can we do? Okay, so we drop the base, we bring down the exponents. 8x minus 1 is equal to 6x.
Oh my goodness, I think
Oh,
it's gonna
look
give
at
the
this
same
answer. Okay. Just because my 18 and 19 had the same answers doesn't mean that y'all's will.
But a
okay?
lot of these problems
But-
do regenerate. I looked through them and there were two
Okay.
that are the same and I changed them.
I'm going to move that 6 over and combine it with that 8x. What's it going to give me? 2x. 8x minus 6x is 2x equals, here, 1, to give me a final answer of 1/2. That's just a coincidence. Any questions?
I was more interested in not having the same numbers. I should have worked it in my head to see if they would
No,
get it
you
the
don't
same
need
answer.
to.
Like 20 we've already done.
21.
Ready for 21.
Oh,
So we grouped
there's-
all the three E's together.
Here
okay?
in this lecture, they're not all together
In
there.
the homework.
But if you're wondering, why are we moving around the way we
I'll
are?
one over in red. That'll give them a good.
To the negative x is equal to 1 over,
Is that an
e to the sixth,
No, it's an E to the B.
6, and
X
x
plus
plus 5. If you view an example on this, I imagine they do this differently from what I'm going to do, but
That
I
doesn't
don't like my base to be, I don't like a base to be a fraction.
If there's an E, the E should be the base.
If there's an E appearing as part of the base, E should be the base. Okay? I want a base of, still have that minus x, and that's the x plus 5. I want a power of E. I don't want a power of 1 over E. I want my base to be, well, I don't want it to be a fraction. And using negative exponents, I can prevent it from being a fraction. Let's do this one first. Let's do the 1 over e to the 6th. Let's just write that as a power of e.
Going all the way back to the
Going
first
back to the
page.
first page of notes today.
Almost there.
There it is. Let's see. 1 over e to the 6th. 1 over e to the 6th. To go backwards, that red 1 over, we drop it. And what does that become over here? A negative. So that'll be a negative 6. The 1 over I drop, the exponent became negative. You say that this thing doesn't have an exponent. Sure it does. If I don't see an exponent, there's always an assumed exponent of 1.
Tim, you said that, but your hearing must be good because I never heard them say that. That there's not an X. You said you say there's no exponent here.
Well, they think. I
Oh.
was reading their mind, and that's what they were thinking. Okay.
Mind reading.
Yes, it's mind reading Wednesday. I try not to show that talent very often because there have been some kidnap attempts when people realize I can read minds, hostile governments and stuff, so hostile countries' governments. So. Anyway,
He's just
I'm
talking
going to drop the
nonsense.
1
They're gonna
over.
tell
I'm
you.
waiting for them to tell me. We're getting close to the end of this long assignment, okay? So now I can start slowing down.
No, because the last two I'm going to do.
Oh, okay. So, well, either way, I'm waiting. I did this side here. The 1 over e to the 6th I wrote as an e to the negative 6. The 1 over e to the 1st we'll write as e to the negative 1. I agree. Any questions? That's the tricky part, in my opinion, right here. Rewriting it so you have your bases of e. Because now we have powers raised to powers. We know what we do to get rid of a power raised to a power. What are we going to do? There's an e. What we do here? Okay, negative 1 times negative x gives me a positive 1x. Over here? Okay, so you're distributing the negative 6 times x. That gives me a negative 6x. What else? And negative 6 times positive 5 gives me a negative 30. Any questions?
See, you took something that looked dramatically different from the other two and rewrote them so they look very much like 18 and 19.
Yeah. What do we do now? We drop the base, set the exponents equal. I think I'd move this minus 6x to the left by adding 6x. What's that going to give me? 7x, I agree, equals, hey, we have a negative 30 there.
Why are you so sharp?
I mean, we don't have anything to combine.
Oh, yeah.
And then
Divide by 7.
divide by 7. Okay, divide by 7 to give us x equals negative 30 over 7. Are you sure I didn't miscopy this problem? I was expecting an integer solution, so
Let's see. 1 over e.
1 over e to the negative x equals 1 over e to the 6th to the x plus 5.
Well,
No, I
know what you
didn't.
messed up. I'll just type it in. I forgot what the answer was. 30 over 7?
Negative.
Negative 30 slash 7.
Any questions there?
Go ahead and start, but I'm going to do it from the ready day.
Okay, I'm ready.
No, you keep on going. For
Oh,
number 22.
okay. Let's look at number 22.
Once you get it in the 22 and 23, the last two have square roots in them. Okay?
I told y'all earlier we were doing those problems where there were radicals and we had to rewrite it using an exponent, and I said you have to add that to your bag of tricks. That's what we're going to do with logarithms. Whenever we run into a logarithm that has a radical, you're going to have to rewrite it using one of those fractional exponents. So that's what we're going to have to do here. We have a red square root of 3, and we have an exponent of x plus 9 on the outside is equal to 27 to the power x.
Well, the common base, what do y'all think the common base is going to be? Well, we have two bases, a 3 and a 27. If you see a radical, the first thing you need to do is rewrite that radical using an exponent. So let's start with the square root of 3. I want to write it with just a 3. I don't want a square root. So how do I rewrite a square root with an exponent? That was on the second page. Oh, 10. Oh, wait. Thank you. There. Okay. A square root is a 1/2 exponent. Okay? Look right here. The fifth root, the square root of 5. The reason you were doing that problem is to get ready for something like this. The square root of 3, I'm going to replace the red square root with what red fraction? 1/2 to the x plus 9 power equals, now, why did I put a red there? Ooh,
3 is a prime number. You better be able to write this number as a power of 3 because you're not changing the left side. That 3 can't be changed. It's prime. So you better be able to write 27 as 3 to a power.
How many
3
threes?
to what power gives you 27?
How many 3's do you multiply together to get 27? 3 times 3 is 9, times one more 3 is...
27.
So-
3 cubed is 27.
So I've rewritten the square root of 3 as 3 to the 1/2. I've rewritten the 27 as 3 cubed. And now we need to multiply to get rid of the parentheses. Like over here on the right hand side, it'd just be 3 to the 3x power. And on the right hand side, normally we distribute, but let's not this time. I'm going to wait to distribute. Look at how I'm going to solve this. You could distribute the 1/2, but you're picking up 2 fractions. Then after you do that, you're going to want to get rid of the fractions. So what I'm going to do is just drop the 3's and write 1/2 times x plus 9 equals, does anyone have any idea what I'm about to write here? I've dropped the big 3's, not all the 3's, just 3x.
Right.
And now I'm going to get rid of the fraction right now. I'm not distributing a 2. We know how to get rid of fractions. Multiply, to get rid of this denominator here, I'm going to multiply both sides by what? By 2. Multiply both sides by 2. So that 2 cancels.
And what are you going to have to distribute over the x plus 9? Just a 1, so I like this better. Normally I distribute the 1/2 and get 1/2 x plus 9/2. Then I have to multiply everything through by 2. But here it saves us from any of that fractional arithmetic. Any questions? We multiplied both sides by 2 to cancel that denominator. We then add a 1 over 1 to distribute over the x plus 9. Well, that just left us an x plus 9.
Now, how would I finish this up?
I do it so that I pick up fewer negatives.
Yep, I think I'm going to subtract x from both sides. So on the right I have the 9, left I have the 9. But what about on the right? The 6x minus x is 5x. And then divide both sides by 5. 9 over 5. So if it involves distributing a fraction here, I think it's probably easier just to wait and multiply through by that denominator.
But I'm betting at all the other videos. I know
Normally
I'd always
I do.
distribute the 1/2.
I've been sitting here
and then
thinking
go
about
through
doing it
multiplying.
like that.
I like this better. Okay, wait a minute. I have to type in that answer of yours. Make sure you
9
didn't
over
get it
5.
wrong. 9 over 5. Yeah, you were right. I figured you were, Tony, but I just wanted to check. Anyway. Oh, here's another one.
This is the last one. So
The square root of 2, all raised to the x plus 6 power.
okay, the square root of 2 raised to the x plus 6 power.
Equals 16 to the x.
I looked at this before class, and they were the same problem. So if you look up at the red x, I clicked on help me solve it so it would change the numbers. Okay. Tell me. Okay. Well, what's the first thing I'm going to do? Have we done anything like this one? Well, I'm
You're
going
going to have to add this to your bag of tricks for logarithms. You may as well do it now for exponentials. If you see a radical, you must first rewrite it using what? A rational exponent.
A fraction.
Fractional exponent.
So this square root of 2 is going to be 2 to the 1/2.
2 is a prime number. You are not going to change that 2 there. You're going to have to write 16 as 2 to the power. That's why you couldn't have 17 there.
I don't say 8. How many 2's do we multiply together to get 16?
4, I agree.
Mm-hmm.
2 times 2 times 2 times 2 gives me 4. Gives me 16.
This step right up here on this one, that step right there, I'm skipping now. I'm going to go straight to drop the 2 and just write what we have as the exponent. 1/2 times x plus 6
What's he going to have on the right
equals.
side? What does he have here?
I'm just looking at the.
Anyone? 4x. That's right. 4
Oh, I didn't
times
hear
x
that.
is 4x.
Good ear.
That's all her lips made.
Oh, you read her lips. Okay.
In
wow.
addition to mind reading, lip reading is another one of my talents.
Oh, okay. Wow. What am I going to do now?
You're gonna
Multiply both sides by 2. That just gets rid of all the fractions.
So what have we got on the left side? Well, he's writing. Y'all tell me what we have on the right side. 8x.
Any questions up to this part? Because the hardest part is yet to come. Not really.
No.
What am I going to do?
subtract the x.
Okay, subtract x from both sides. I have 6 equals.
What has he got here?
7x.
8x minus 1x is 7x. I agree. And then
Divide
Divide
by
by
7. So 6 over 7.
any questions?
Punch that in. We'll have 100. And this longest, it's not that hard. It's not like every problem on here is hard. These last ones like this, they take some thought. And you're learning these new techniques. Rewrite a square root as a 1/2 exponent and stuff. You know, but any questions?
Do y'all see this problem number 23 would have been impossible if that 16 had been a 17? Because no matter what, you've got to be able to get the same
Common
base on
base.
both sides. 2 to no integer power is going to give you 16. You'd have to use logarithms. We have a very nice little method for solving using logarithms when there's an unlike base. But
On Monday, try to do these problems before
okay,
Monday.
any questions? I'm about to stop recording.
Okay, stop recording.